Welcome to Kenton's videos. Enjoy the video.
You start by gathering parts and making the first electrical and mechanical connections so you can get measurable signals. The Y is speed and alignment precision. First, solder the laser driver and photodiode to the PCB, then attach the microcontroller with SPI or UART for data. Once done, mount the emitter and receiver on a rigid bracket with adjustable shims so you can fine-tune optical overlap. Make sure to wire the rotary encoder and motor with proper decoupling capacitors to avoid noise. You now focus on capturing and processing return signals because timing defines distance accuracy. Start by designing the analog front end: a transimpedance amplifier, anti-alias filter, and programmable gain so you can tune sensitivity. Then program the microcontroller to trigger the laser synchronized to encoder pulses. Use DMA for continuous samples and interrupts for frame boundaries. Once done, implement a simple peak detection or cross-correlation algorithm to extract time delays, and you finish by calibrating and turning raw timings into a usable point cloud so the sensor is meaningful. First, capture multiple measurements at known distances and angles to compute bias, scale, and temperature compensation. Apply corrections in firmware. Next, transform polar coordinates to Cartesian using encoder angles and filter outliers with median smoothing. Finally, validate performance on real targets. If you see missing points or excessive noise, reduce analog bandwidth, increase laser pulse energy, or tighten optical alignment. This single troubleshooting tip often fixes most issues.
Thanks for watching. Consider subscribing if we helped you.